Welcome to this exploration of one of the most profound and humbling theorems in machine learning. The no free lunch theorem. This fundamental principle tells us that there is no universally superior algorithm that works best on every problem. Understanding this theorem is crucial for any data scientist or machine learning practitioner, as it shapes how we approach algorithm selection and problem solving. The no free lunch theorem states that when averaged over all possible problems, every algorithm performs equally well. This means that if algorithm A outperforms algorithm B on some problems, then algorithm B must outperform algorithm A on other problems by an equal amount. There is no free lunch. No algorithm gets to be universally superior without paying a price. Elsewhere, imagine a restaurant competition where different chefs must cook various cuisines. Each table represents a different type of problem: Italian food, sushi, barbecue, desserts, and breakfast. The chefs represent different algorithms. Here are their performance scores. Chef A excels at Italian cuisine but struggles with sushi and desserts. Chef B dominates sushi and desserts but is mediocre at barbecue. Chef C shines at barbecue and breakfast but is average elsewhere. Notice how each chef has strengths and weaknesses. When we calculate the average performance across all cuisines, something remarkable happens. All chefs have nearly identical average scores. This is the essence of the no free lunch theorem. Superior performance on some problems is balanced by inferior performance on others. Let's examine the formal mathematical statement of the no free lunch theorem. This theorem applies to both optimization and machine learning, providing a rigorous foundation for understanding algorithm performance. The formal statement says that when summed over all possible functions, the probability distribution of performance is identical for any two algorithms. This means that, averaged over all problems, every algorithm performs exactly the same. The key insight is, all possible functions. This includes not just real-world problems, but all mathematical functions. Here's the intuitive understanding. Every algorithm makes assumptions about the problem structure. These assumptions help when they match reality but hurt when they don't. Since the space of all possible problems is vast and unstructured, good performance on some problems must be balanced by poor performance on others. This is why no algorithm can be universally superior. Let's see the no free lunch theorem in action with real machine learning algorithms on different types of problems. We'll compare how various algorithms perform on different dataset structures to illustrate the theorem's principles. We'll test 5 different algorithms on 4 different problem types. Each algorithm has different assumptions about the data structure. Linear regression assumes linear relationships. Decision trees assume axis-aligned splits. SVM with RBF kernel can handle complex boundaries. KNN assumes local similarity. And random forest combines multiple decision trees. Let's visualize the 4 different types of problems we'll use to test our algorithms. Each represents a different challenge that favors different algorithmic approaches. Here are our 4 problem types. Linear separable data where classes can be divided by a straight line. Circular boundary where one class surrounds the other. Complex nonlinear data with moon-shaped clusters. And finally, noisy data where there's no clear pattern. Each favors different algorithms. Now let's see how different algorithms perform on each problem type. The performance matrix will reveal the no free lunch principle in action. No algorithm dominates across all problem types. Here's the performance matrix with color coding. Green indicates excellent performance above 85%. Yellow indicates good performance above 70%. and red indicates poor performance below 70%. Notice how each algorithm has its strengths and weaknesses. When we calculate the average performance across all problems, we see the no free lunch principle emerging. While there are differences, no algorithm is dramatically superior overall. Linear regression excels on linear problems but fails elsewhere. SVM dominates complex boundaries but struggles with noise. Each algorithm pays for its strengths with weaknesses. The no free lunch theorem has profound implications for machine learning practice. It explains why we need multiple algorithms, why benchmarking is important, and why domain knowledge is crucial for algorithm selection. First, algorithm selection becomes a matching problem. We must align algorithm assumptions with problem characteristics. Second, benchmarking requires diverse problem sets, and claims of superiority need context. Third, research focuses on problem-specific improvements, ensemble methods, and automated algorithm selection rather than seeking one universal solution. Kaggle competitions provide perfect real-world evidence of the no free lunch theorem. Different competitions favor different algorithms, and winning solutions often combine multiple approaches to leverage their individual strengths. Kaggle competitions perfectly illustrate the no free lunch principle. Tabular data competitions are dominated by gradient boosting methods like XGBoost image. Competitions belong to convolutional neural networks. NLP competitions favor transformer models. Time series competitions still see classical methods competing with deep learning. Each domain has its champions, proving no universal winner exists. The no free lunch theorem is often misunderstood or misapplied. Let's address common misconceptions to ensure proper understanding of when and how the theorem applies in practice. First misconception: that all algorithms are equally good in practice. This is false. The theorem applies to all possible problems, but real problems have structure. Second, that there's no point developing new algorithms. Wrong. We can create better algorithms for specific problem classes. Third, that algorithm choice doesn't matter. Actually, matching algorithm assumptions to problem structure is crucial for success. The crucial insight is that while the no free lunch theorem applies to all possible problems, real-world problems are not randomly distributed. They have structure, patterns, and regularities that algorithms can exploit. This Venn diagram illustrates the key point. The outer circle represents all possible mathematical problems, the domain where no free lunch applies. The inner green circle represents real-world problems we actually encounter. These problems have structure. Images have spatial correlations. Text has grammar and meaning. Tabular data has feature relationships. This structure allows algorithms to be better than random. Real-world data has rich structure that algorithms can exploit. Images have spatial locality and hierarchical features. Text follows grammar and semantic rules. Financial data shows trends and seasonality. Medical data reflects biological constraints. Sensor data follows physical laws. This structure is why some algorithms consistently outperform others in specific domains. Understanding the no free lunch theorem leads to practical strategies for machine learning. Instead of seeking one perfect algorithm, we should focus on matching methods to problems and combining multiple approaches. First, deeply understand your problem, analyze data structure, identify valid assumptions, and study successful approaches in your domain. Second, maintain a diverse algorithm portfolio with linear, tree-based, and neural methods. Third, systematically evaluate multiple algorithms using proper cross-validation. never assuming past winners will repeat without testing. Ensemble methods represent a sophisticated response to the no free lunch theorem. By combining multiple algorithms, we can capture different aspects of problem structure and achieve more robust performance across diverse scenarios. Here's how ensemble methods work. Individual algorithms each make predictions based on their own assumptions and strengths. The ensemble combines these predictions using voting, averaging, or more sophisticated methods. The result is a robust prediction that leverages the strengths of multiple approaches while mitigating individual weaknesses. Ensembles work because they combine different algorithmic assumptions, reduce overfitting through averaging, and become more robust to different problem types. They frequently win machine learning competitions and excel in real applications. This reflects the wisdom of Claude's principle. Multiple diverse opinions often outperform any single expert. First, we define a NFL-aware classifier class. The key insight here is maintaining a diverse algorithm portfolio. We include linear methods like logistic regression, tree-based methods, support vector machines, instance-based learning with KNN, and ensemble methods like random forest. This diversity is crucial because different algorithms excel on different problem types, as the no free lunch theorem predicts. The evaluation method embodies the NFL principle by systematically testing all algorithms without bias. We use stratified k-fold cross-validation to get robust performance estimates. Notice how we don't assume any algorithm will be best, we test them all fairly. The try-except block handles cases where algorithms might fail on specific data types, which is another NFL insight. No algorithm works on every possible input. The ensemble creation method represents our strategic response to the no free lunch theorem. Instead of picking just one algorithm, we combine multiple good performers. This voting ensemble leverages the strengths of different algorithms while mitigating individual weaknesses. We use soft voting with probabilities for more nuanced decision making. This approach often outperforms any single algorithm because it captures different aspects of a problem structure. The fit method makes intelligent model selection based on empirical evidence. We compare ensemble performance against the best individual algorithm and choose the superior approach. This data-driven selection embodies NFL thinking. We don't assume ensembles are always better. We test and decide based on performance. The ranking method helps us understand which algorithms work best for specific problems, building intuition for future similar problems. Finally, the demonstration section tests our NFL-aware approach on different problem types. We create linear separable data, circular boundaries, and moon-shaped data, each favoring different algorithms. This directly illustrates the no free lunch principle. Different datasets will show different algorithm rankings. The code automatically adapts to each problem type, selecting the best approach based on empirical evaluation rather than assumptions. Here's the expected output showing the no free lunch theorem in action. Notice how algorithm rankings completely change between datasets. On linear separable data, logistic regression dominates and decision trees perform poorly. But on circular data, SVM with RBF kernel excels while logistic regression fails miserably. This perfectly demonstrates that no algorithm is universally superior. Performance depends entirely on the problem structure. The no free lunch theorem has profound implications for how we approach machine learning in practice. It fundamentally changes how we think about algorithm selection, model development, and performance evaluation. For algorithm selection, always test multiple methods on your specific problem and use domain knowledge to guide choices. For performance evaluation, remember that benchmark results are only valid for similar problem types. For research, focus on understanding when and why methods work rather than seeking universal solutions. For business, maintain diverse toolkits and systems that can adapt as problems evolve. The no free lunch theorem connects to broader philosophical questions about artificial intelligence and machine learning. It teaches us humility, encourages diversity, and reminds us that intelligence is context dependent. The no free lunch theorem teaches us profound lessons. Intelligence is context dependent, just as no algorithm dominates everywhere. Different minds excel at different problems. Diversity creates strength. The theorem mathematically proves that diverse approaches are necessary for robust problem solving. It highlights the eternal trade-off between specialization and generalization. It encourages scientific humility, teaching us to test assumptions rather than assume superiority. Finally, it promotes collaboration over competition, since ensemble methods often outperform individual approaches. Understanding the no free lunch theorem opens up exciting future research directions. Rather than seeking universal algorithms, we can focus on automated algorithm selection, meta-learning, and intelligent problem characterization. Future directions include automated algorithm selection systems that choose the best methods for each problem. Meta-learning focuses on learning to learn, creating algorithms that adapt quickly to new problems. Better problem characterization helps us understand which features predict algorithm success. Adaptive systems can monitor performance and switch methods automatically as conditions change. These directions embrace rather than fight the NFL principle. Let's summarize the key takeaways from the no free lunch theorem. The core principle is that no algorithm is universally superior across all problems. The fundamental trade-off means that superior performance somewhere requires inferior performance elsewhere. The practical wisdom is that real-world problems have structure that algorithms can exploit. The strategic response involves using diverse algorithms, systematic evaluation, and ensemble methods. The philosophical lesson teaches us to embrace diversity, test assumptions, and remain humble about our methods. Here's practical advice for applying NFL principles in your work. Do maintain a diverse algorithm toolkit and always test multiple approaches. Use proper cross-validation and combine methods with ensembles. Study your domain deeply and remain open to different approaches. Avoid assuming one algorithm is always best or relying only on general benchmarks. Don't ignore domain knowledge or use algorithms without understanding their assumptions. Stay curious about all methods, old and new. The no free lunch theorem teaches us that the journey of discovery in machine learning never ends. As Stephen Hawking said, the greatest enemy of knowledge is not ignorance. It is the illusion of knowledge. The NFL theorem reminds us to stay curious about different approaches, test assumptions rather than accepting them. Embrace the diversity of methods and problems. Remember that context always matters. And keep learning, experimenting, and growing in our understanding. Thank you for joining this exploration of the no free lunch theorem. May this knowledge guide you to more thoughtful, diverse, and effective machine learning practices. Remember, there is no free lunch, but there are many wonderful meals to discover when you know where to look. Keep exploring, keep questioning, and remember that the best algorithm is the one that works for your specific problem. Happy learning and experimenting.